Hello, I'm Nick Iliadis. I'm the Vice President of Product Planning at Achronix Semiconductor. Achronix is a supplier of high-performance FPGAs, and today I am here to talk about optimizing IoT with FPGAs, focusing on AI and machine learning breakthroughs that are leveraged through FPGAs. Achronix builds high-end FPGAs. These are the most advanced high-performance FPGAs in the market. They've been optimized for data acceleration and have advanced efficient data transports. One of them is our 2D NOC that we are unique in the industry of having in our devices. We also sell our FPGA technology as intellectual property. This is IP that can be integrated into a customer's system on a chip or ASIC. We call this embedded FPGA technology. So this way a customer can put a FPGA technology into a device that they're building. And we've shipped over 15 million of these cores to our customers who've shipped them in their products. And then we also build acceleration cards that have our FPGAs on them for allow customers to quickly plug these into a server or stand along a bench and run their designs into the card and get performance, and they can even ship the card to the product if they want as well. And then all these are supported by our Achronix tool suite that provides synthesis, verification, timing, programming, and debug. So first of all, for those of you that may not be familiar with an FPGA is really a reprogrammable hardware. It's an integrated circuit that can be programmed or reprogrammed after manufacturing. It has logic, digital signal processing, input-output, and memory that can be configured to perform any digital functions that the customer or user wants to apply in there. And the designs can be modular, and you can implement multiple hardware designs to ensure the FPGA fits into specific systems. And they're typically designed with things like Verilog, VHDL, or System C, and then synthesis tools run on those, and then we have our own place and route that allows you to program the FPGA, and these can be reprogrammed in the field to whatever functionality is needed. So it's a very flexible hardware that allows you to reconfigure it after it's been shipped out. So looking at AI and machine learning for IoT, the area I'd like to focus on is the 6G network that's now being defined through different standards and industry consortia. The AI/ML is really broken into, let's say, these domains, one of them being the on-device, meaning all the things that are either accelerated on the device or are being implemented on the device or displayed on the device. And then there are the domains are in the network. There's the neural edge, which is typically what is deployed out in the network, the base stations, the antenna arrays. And then there's what's called the neural center, which is what's running in the cloud data centers, or the let's say data centers that are co-located near the service points. And today, Achronix provides solutions for both the neural center and the neural edge, and I'll go into both those in more detail. So, low latency in the neural center. So one of the things that impacts, let's say, user, positive experience with AI/ML is latency. So if you basically are doing something and it takes a long time for the response to come back, people tend to get impatient, or the interactivity suffers. So latency has become a very key attribute of AI/ML to allow much more natural interactions. So the neural center hosts end user applications in either hyperscale data centers, central offices, or other remote locations. And there are three main components of the latency that is experienced. There is the network latency, which is the time it takes for data to travel from the network, from the user to the data center and back. So that's kind of a round trip delay. There is the server latency, which is basically the time it takes for the data to enter the server, get processed by the networking cards, the CPUs. And then there's the application latency. and that is what actually processes the data, applies the any type of neural algorithms, any type of other software to that, and that is also a component of the overall latency that is experienced by the user. So hardware acceleration can improve the server and application latency because it can offload things that are being done in the CPU that can be done better in hardware, dedicated hardware in this case. So one of the use cases that we've been developing with one of our partners, Myrtle.ai, is conversational AI. And what conversational AI has to do with is the reception of human speech, the decoding of it into text, feeding that text into some sort of a natural language processing or generative AI model, and then in turn taking the response of that and generating speech, audio speech that can then be played back to the user. So the whole idea here is to interact with the computer as though it was human. You say something, and then there is a response back with whether you asked a question, whether it was a follow-up, response to the previous interaction. But all those things happen much more naturally if the latency has been reduced, because then people aren't sitting there waiting. Did they hear it? Was I heard? Did you understand it? So the fact that you're able to come back quickly with a response makes it much more natural, and that's why it's called natural language processing. So where would conversational AI be applied? There's a lot of different areas. Language translation is one where if you want to be able to speak to somebody and have your speech translated real time, again, latency becomes a very key component of that. Virtual assistants, if you're asking a virtual assistant some questions, you want to get responses back as quickly as possible, again, to close that loop, as they say, right? And then closed captioning is another one. Areas such as maybe hearing impaired people being able to see the text on their phone as they're having a conversation with somebody in real time, right? So these are all areas where latency becomes a key component. And what does an ASR solution look like? The one that we've developed is basically our partner Myrtle with their software and AI models, a server workstation, and then the FPGA card that I showed you earlier in the presentation, which hosts our device. And this basically, the three of these together provide a appliance, let's call it, that allows you to bring your audio in and get the responses out. This for the speech to text portion of this is a block diagram of the speech to text, where you basically have a website get API which feeds some audio processing inside of the CPU, but then the heavy lifting is done by the FPGA accelerator, which is sitting in that same server, but now is taking the audio files and very quickly converting them into text. And to show you how well we do that, you can see here we compared our performance against a NVIDIA A100 running a conformer model, where the Speedster 7T is running in RNNT, which is a recursive neural network. And you can see here, as the number of streams that are supported by our hardware goes up and to the right, the latency slope is fairly low, and we're at around 50 milliseconds for the 99th percentile, whereas the NVIDIA goes up fairly quickly as you add more and more streams to the processing. So we see about the 7x throughput improvement and an 8x latency improvement when compared to a standard GPU doing this type of computation, or as I say, conversion from audio to text. So how is this achieved? So the device that's on that card is our 7T1500, Speedster 7T1500. It has enhanced AI ML processing blocks. So it has hardware blocks within this FPGA fabric that are basically math engines that are optimized for machine learning. It has high-speed I/O to bring data in and out of the device. It has networking protocols, so if you want to actually use it sitting on a network directly attached to with the sources, it can do that. High-speed memories for storing all the machine learning activation and weights. One of our defining features is our network on chip, our 2D NoC, which provides 20 terabits of interconnect across the entire fabric, as well as PCI interfaces to get data in and out of the computer. So this is a very high performance device. This has been shipping now for several years and is available, like I said, on a card for evaluation or even productization purposes. So we talked about kind of the neural center, which is the things running in the data center. These can be very scaled up. It can be supporting thousands and thousands of users. But there's also what's running in the neural edge. So this is the radio network, what is actually touching the devices that are sitting out into the in the field. And as the processing of the radio processing, is really tied to the number of the bandwidth and the number of streams that you're running back and forth between the end users, like UEs, and the base stations, the antenna arrays. And you can see here as you go from 20 megahertz bandwidths up to 100 and 400 megahertz bandwidths, and 128 or 256 transmit streams and receive streams. The amount of processing that's happening, especially as you get closer and closer to the actual antenna, L1 processing, beamforming, and then you see machine learning there all of a sudden go from virtually nothing in the lower bandwidths to now being a significant amount of operations per second that are being applied there. And the question is, where does machine learning actually play a part in the this radio network? So where does it add value? And one of the key use cases here is massive MIMO. As I was showing all those streams in the previous page, those streams really equate to beamformed connections between user equipment and the antenna arrays. And these can be tens or hundreds of antennas that are simultaneously transmitting, but are transmitting in very narrow beams that are being targeted to individual users for that particular connection, but that connection can then be moved to another user if it's idle, right? So this is coordinating and orchestrating many beams across the network here. You can see here, this is a kind of a block processing chain between what's happening at the transmitter and what's happening at the receiver. And the receiver has a lot of functions that do with receiving an optimal signal. And one of these is called channel estimation. And channel estimation is really understanding what is the channel that I am communicating, this device is communicating with an end user to allow me to give it the optimal power, the optimal focus on that beam in terms of where it's being sent. And so that can be computationally heavy because you sometimes have to exchange information with the UE to understand what that channel is, or it can be based on learning. So that receiver can have learned over a period of time. If I have a user device that's in this kind of general location, I've already learned what that channel response would be, and based upon a historical tracking, I can now anticipate what that channel is going to look like based upon history. This is what we call a time-varying signal that varies over time, but can be potentially predicted based upon past history, right? So this company that we are partnering with, Myrtle.ai, also has small models. The one I was showing earlier for natural language processing are these large models that can do thousands and thousands of streams. But there are these small models that are really optimized for latency and size. In this case, we're showing you here a window of 10 microseconds, where there's 3 different neural networks here that are being processed with almost 300,000 parameters, 4.9 million parameters, or 3.1 million parameters, and they're being processed in under 10 microseconds. So now this gives you the ability in a radio network to be very agile and also very quick in terms of how you adapt the transmission and reception to the environment. So how would that be implemented in a radio or a kind of a base station? Other than our standalone products, we also, like I said, sell our intellectual property, our FPGA fabric, as IP. So a radio manufacturer or a base station manufacturer could take that FPGA IP, incorporate it into their baseband ASIC or SoC as an FPGA fabric that's inside of their radio device to provide this let's say, machine learning algorithms that can be changed and adapted over time. And this provides, today we have the technology available in 16 nanometer, 12 nanometer, 7 nanometer, and working on even more advanced nodes. And today we're the only supplier that supplies not only standalone parts, but also the same technology as IP that customers can incorporate in their products. So if you want to get more information, there's a link here to our website. You can register online. You can get a free evaluation license for our design tools, and you can see some demos there as well. I want to thank you for listening and look forward to your questions.